Hello everyone. So let's get back to my channel once again. Uh, there is a long delay of this channel, and I am doing a video after a long time. It was due to some personal reasons, but yeah, good to see you all also, and I am also back on my channel. So I was doing a series. I was doing a series on electronics, mainly, especially digital electronics. So that was a part where I'm just doing some fun activities last. Okay, so next I think I will start a series on advanced quantum mechanics in this new segment about that how quantum mechanics evolved and how quantum mechanics become old to new one. We all know from the uh, quantum mechanics part, but we don't know about uh, the advanced quantum mechanics. Those people who don't know about the advanced quantum mechanics, the application of the quantum mechanics in some extent, in some greater extent. So those we will start from this class 1 and from this video. Okay, so first of all we will discuss about the time independent perturbation theory. In this advanced quantum mechanics we will discuss about three topics. One is perturbation theory. There is two types of perturbation theory: time independent and time dependent perturbation theories. And another two things are variational principle and uh, variational principle, and there is and the scattering effect. Okay, so perturbation theory, variation principle, and the scattering theory of scattering theory. These are the main three topics of advanced quantum mechanics. So first we will start from time independent perturbation theory. So let's dive into it. Okay. So first we will discuss about time independent perturbation theory. So to proceed to the time independent perturbation theory, I will suggest about to read about potential wells, concept of potential wells in the quantum mechanics segment. I personally did some videos on the on this basic quantum mechanics in past, but those were in some sorry in Bengali language. But if you have knowledge about the potential well, so you can start from the beginning. But I just once just one in one or single one or two lines I will explain what is the potential well exactly, and what is the theory behind it. Okay, so what happens is that we know all about the crystal structure, that there is some crystal points here. Those are called bases, and there is some crystal over here to make a regular arrangement of periodic crystal structure. Okay, so each of the atom has corresponding potential well, just like that. Okay. In astronomy also, when sun has also a corresponding potential, and when earth is revolving around the earth has also its corresponding potential well. So this is called a potential well, and to calculate everything in a manner of in easy manner, we will make this to approximately as a rectangular shaped well. Okay, so this is the main concept of potential well, like that. So this is the main potential well concept, which has some height and some width, okay, depending on the atoms. Okay, so then perturbation occurs means there is there are four steps to apply perturbation on a system. Let's discuss one by one. So let's consider as this is the atomic structure and this is the corresponding potential corresponding to this atom. Okay, so there are four paths to apply perturbation: by applying heat, applying electric field, applying magnetic field, and another is optical field, applying some very high frequency rays. Okay, so when a very high frequency wave is applied on the potential, then the real potential got perturbed, and from there we need to explain the scenario using the perturbation theory. So next we will discuss about what is wave function. So next question is, what is the wave function? We know that in the basic quantum mechanics there is something called psi, in which we can get that have all the dynamical properties about the wave. Okay, and if we operate any operator on that, we will get its corresponding physical entity as eigenvalue, right? Eigenvalue. So when such like we will operate Hamiltonian operator on psi, we will get the energy, total energy, as the eigenvalue of the system of wave function psi. So if there is n number of waves, n number of eigenstates, then corresponding energies will be n number of eigenvalues. So this is the required Schrodinger equation, and which will be the mother of all the derivations of this perturbation theory. And what happens is that the perturbation occurs in pictorial view. This is the potential well. Let's have a kink here. So if there is a kink here, we have to then derive using the perturbation theory. So when there is no perturbation, we will define as H0 psi n0 equal to En0 psi n0. So when talking about a system without perturbation theory, we will have to demonstrate just only the wave function and get the eigenvalue corresponding that eigenstate. But when it comes to perturbation theory, then we have to compare about the system's unperturbed state and perturbed state. So when this is the unperturbed state, we will discuss about the system. Then we will use this equation as this, and there is a orthonormality condition also there, that is psi n0 psi m0 is delta mn. We all know delta mn equal to 1 when m equal to n, and equal to 0 when n not equal to n. So this condition also matters. So when this kink come, so we have to use the perturbation theory to solve the equation, Schrodinger equation for the corresponding system. So let's begin the perturbation theory. So let's discuss about the perturbation theory with a potential well having a kink on it. So then the Hamiltonian will become like this: unperturbed state plus lambda into h prime. H prime is the perturbed state's Hamiltonian, lambda is such thing like the value between 0 or 1. We will crank this lambda's value 0 or 1 and will get the perturbed Hamiltonian. If there is no perturbation, lambda will be 0. If there is some extent perturbation, that it will be greater than 0 or hardly 1. Okay. So let's have a series solution here. So let's extend psi m as psi n0 plus lambda psi n1 plus lambda square second order perturbation dot dot dot. Corresponding energy eigenstates will be En0 plus lambda En1 plus lambda square En2 plus dot dot dot. So now we will operate this thing on this and we will get the energy eigenstates. Okay. So next it will be H0 plus lambda H prime. It will be operated on this one. Psi n0 plus lambda psi n1 plus lambda square psi n square is equal to En0 plus lambda En1 plus En square lambda square equal to psi n 0 lambda psi n 1 plus lambda square psi n 2 dot dot. So finally we will get by multiplying those we will get a coefficients of lambda and lambda square. So let's see what will be the coefficients of lambda and lambda square from this equation. So there are the two equations corresponding the coefficients of lambda and lambda square respectively from the past equation, and these two equations I have named as A and B. So we can derive the first order and the second order perturbation theories respectively from using these two equations. Okay, so next we will start about first order theory, perturbation theory, and next we will end this session by doing second order theory. So in equation A, from equation A, if we do a inner product with psi n0, we on equation A, then we will get like that psi n0, it's called bra, and corresponding we will get the ket here, and here also psi n0 bra h prime psi n ket 0, and corresponding we will get on the right hand side also. Then we will get psi n0 en0 psi n1 plus psi n0 en1 psi n0. So from the orthonormality condition we will get the energy eigenvalue, first order energy eigenvalue as psi n0 h prime psi n0. So from the part of Hamiltonian we will get the energy eigenvalue about the first order perturbation theory. Next from A we will get H0 plus En0 psi n1 and minus H1, sorry, this will be H prime minus En1 psi n0. And we know that there is a psi 1, it will be a complete set of CSCO, complete set of complementary objects, something is that CSA, complete set. So it will have a normalized coefficient. So from the initial wave function we can, from the final wave function or perturbed wave function, we can get the initial unperturbed wave function from this equation. And if we put this equation onto this, then we will finally get Okay, so from this we again do a inner product with psi L0 with on that equation, and this will give the value of the coefficient. We need the coefficient first, so the value of coefficient will be psi m 0 h prime psi n 0 divided by en 0 minus em 0. So m must be not equal to n. So this is a non-degenerate case. If there is degenerate case, same equal to n, then that will be another thing that will be discussed in the next videos probably. So finally we will get the wave function. So finally the equation, the wave function of first order perturbation theory will be summation over m not equal to n psi m 0 h prime psi n 0 en 0 minus em 0 psi m 0. So this is the required first order theory. Next we will cover the second order theory. So let's have a inner product on B. We will get en2 psi 0 n h prime by psi n1 minus en1 psi n 0 psi n1, and this inner product will give us en2 m not equal to n cmn psi n 0 h prime psi m 0. That will be summation over m not equal to n psi m. We know the value of this complex coefficient, so we will just put it on this equation, and the both will be same. Just mod square complex conjugate, it's complex conjugate, we all know, and divided by en0 minus em0. So finally we will get the second order energy. So the final equation will be en square summation over m not equal to n complex conjugates are getting squared mod square divided by again both are non-degenerate state. So this is the final expression for the first order and second order perturbation theory. Hope you will all enjoy this lecture. Next I will cover next further topics of the perturbation theory. Till then, please stay tuned. Thank you.